two speakers for today. I'm really excited about these talks. We're going to start off with Sudhakar Pamidighantam from Indiana University. He's going to be talking about the AMPGateway, a portal for atomic, molecular, and optical physics simulations. And then from San Diego Supercomputer Center, Igor Spiligoy, talking about bursting into the public cloud, his experiences doing it at large scale for IceCube. So I'm going to go ahead and stop sharing. So Sudhakar, take it away.
Okay, thanks, Bob. Let me start sharing here. Go to slide mode. You're all seeing it, okay?
Yep.
Okay, so hope you're all safe and sound. So we'll continue. So, I mean, this is a talk that I, part of it was given at the NIST workshop that we conducted recently, end of December. And also I gathered some of the content from the other speakers. And this is a slightly modified talk in that sense. So this talks about a science gateway, what we call atomic, molecular, and photophysics kind of gateway. So I'll talk about these application drivers. Of course, scientific applications are the driving force for all our activity. So we'll talk about where this gateway comes into picture. So of course, allocations of resources are important, and I'll just very briefly mention that. I'll talk about the scientific applications briefly, and then talk about how the gateway was formed. There will be, of course, some information about what are the requirements for these gateways in general, and I'll summarize and tell what we are looking at going into the future. So so this is supposed to be an acknowledgement side, but I thought I may not get to it at the end, so I just put it up on top. Barry Schneider is the PI for this gateway. He works at NIST, and he also contributes a software called MESA. And I just listed a bunch of applications. We'll see them again. It's an international group of scientists that contributed to this gateway. You see all kinds of continents represented here. And the Science Gateway, of course, we are part of Cyber Infrastructure Integration Research Center at Indiana University, and all my colleagues who I didn't mention by name here, but they're all contributed to this one way or the other. Of course, NSF funds some of these activities. And XSEDE ECSS was significant, and so on and so forth. And we use this technology called Apache Airavata, which I will mention, and SciGap as a project. So the AMP Science Gateway, was conceived by Barry at NIST to look at, bringing these applications together. So these applications, are specifically for atomic and molecular physics. So they want to look at electron scattering and photo processes. So that means that there's excitation potentially, and how particles interact with each other, particularly small particles like electron and positron, and interactions with atoms and molecules. So they want to predict how this interactions will be and compare with experiments. So there are again, since excitation is mentioned, electromagnetic radiation is always there, and it could be explicitly added to the system, and then we need to be able to predict these properties. There is applications of these in fusion, astrophysics, and so on and so forth. I think I mentioned this again in a later slide. So there are significant applications, and our understanding about this process is very, very important. And so there were a lot of discussions in the atomic and molecular physics community about bringing these software and communities together into a platform where they can share, they can contribute, they can test, and train, and so on and so forth. So, and that's the major vision. There is also a vision to make these applications portable tested, and so on. And as part of that, of course, the atomic physics community is at the forefront of software engineering and other technologies to enhance the in creating the software as well as distributing and providing this, but they didn't have a platform where everything is together. And so that's where we started to create the gateway and get some resources dedicated to it. And so this gateway, of course, is going to bring the applications into this platform and potentially workflows. I'll show some of those workflows in this presentation. And of course, we want to bring the community to the applications and resources to the communities. And of course, we want to deploy collaboration tools and get feedback from the community and sustain these operations in a smooth fashion. Okay, so the main applications are provided here and some allocations. So initially we started with a startup allocation on XSEDE, and then later I think we have what's called a discretionary allocation at this point on Comet, Stampede, and Frontera. And a community login was generated for this gateway, and we are currently using that. So this AMPGateway is now in production. Many applications are deployed, and some of these applications are listed here. We'll talk about these in detail further. So, coming back to what this gateway in general needs, and or what could be the process in generating such scientific application gateways is kind of mentioned here. This is a kind of a general requirement. People who may be interested in creating such gateways for their own applications, or they can think of providing portals for enhancing science or training and things like that. So these are some general requirements. So I mean, some high performance computing system need to be registered so that these applications actually can run on these gateways. So in this case, we have a super gateway called SciGap, which helps to host all the other gateways. So this is like a multi-tenanted system that hosts many gateways, and AMPGateway is one of them. And there is a registration of resources in that is needed here. And the applications, of course, should be installed somehow or the other on the high performance computing systems that are registered in this hosting service. So this is like it could be an out of band process, or it could be part of the gateway process itself. I mean, you can think of continuous deployment type schemes where you can take a Docker and deposit it, or a Docker image of the application, or you can explicitly take the code and compile and so on and so forth. So in this case, we actually took several of these codes and compiled them on many platforms, Stampede 2, Comet, etc. And of course, we need to identify the inputs and of course the outputs. And in some cases, what we need to do is to actually wrap some of these applications so that certain pre and post processing can be managed to smoothen the interaction for the users. And again, so outputs need to be parsed and the data extracted so that a nice presentation is provided to the user. So we need to also think about creating archives and storage for this data. Sometimes it is not just a simple output that is generated when an application is executed. It could be a large amount of output that need to be processed in subsequent steps. It may not be a single workflow that can complete all the analysis. There may be multiple workflows that need the data generated. So that's why an archival process is also important. So user interfaces need to be designed. So, I mean, how user interacts with these applications in the gateway, both, in the input process as well as the output, that is the post-processing. So there are some nuances with this post-processing that could be considered. We'll talk about that down the line. And of course, gateway identity. Some identity needs to be created. In this case, we call it AMPGateway. I mean, so I mean, for atomic and molecular physics, there are already divisions in the physics community called AMP that are in the APS, for example, American Physical Society. So that AMP is a common, kind of a quickly recognizable word, and it is easily identified. And naming the gateway is, in such sense, is probably important. And of course, we need to come up with a theme for the landing pages for this gateway. Of course, the gateway itself need to be registered, in some registration process. I think Barry went to GoDaddy to register this one. And so once this is done, then of course, if we have a community login, then it needs to be organized, and we need to have a process to get to the community login. For many individuals that come to the gateway, there is a single login that kind of is used to enable several automated processes. And of course, this community login is not strictly needed, but it helps for community to a large extent. And of course, allocations are needed, and then we have to deploy applications as a and user interfaces, and then tie all of these things together. Of course, we have to test and provide them to the users. So there are other applications, adjunct for analysis, or input preparation, and so on and so forth, that may also be needed. We need to create documentation, create support structures if there is a problem with what happens on the gateway. Somebody needs to address those problems, troubleshooting and so on. Of course, we have to talk about analytics. How many people are using the gateway, what kind of functions they are using, which application. I mean, all those things are important. And then, of course, we have to set the user's expectations. For example, some people who submit a job, they expect the output to be immediately, available. For some of these, of course, physics applications, these things could be running for a long time, and then they need to know that, they can go for a coffee and come back and, look at the results. And those expectations are very important, because I mean, unless if there is a wrong expectation, the interest with the gateway may change. And of course, a lot of community building is important. These workshops that we create, the training events, and so on and so forth are critical in building and sustaining a community, because these are community built tools and built for communities. It is like by communities, for communities, and so on. And of course, we need to, of course, track usage of these gateways, to track the publications, highlights, provided on the gateway, and so on and so forth, will sustain the interest. And of course, periodically we have to survey the community about the new requirements, and change the gateway and how it operates, and so on. And of course, funding is very important. So I mean, individually, all of these contributors to the gateway have their own funding, and particularly this is an international group of scientists, as I mentioned. But the gateway itself is currently not funded. I mean, so we just started this operation through a startup allocation, as I mentioned, and now we are actually thinking about applying for some funding. So briefly about the applications. As I said, this is about scattering of electrons and other particles on atoms and molecules. And so there are various kinds of processes that I kind of listed here as as reactions. There is a system called AB, and an electron scatters on it, either interacts with it, and it scatters away. So that's one process. or it excites, once the electron impinges on some system, it can excite the system, and then there is a modification. I mean, so this electron, the first one and the second one are slightly different. There could be resonance, an electron could be embedded, there is a photon that can come out of it, and they could be coupled with other processes in the system, like vibrational modes of the atoms in the molecules. And all these things require science that can actually probe and extract information at an electron, at a very small particle level, at atoms and electrons and so on and so forth, and requires quantum mechanics, and they're expensive and very difficult to study. In general, of course, there's some, of course, theory available, and the kinds of particles could be electrons, positrons, and so and other particles. So the applications, I just mentioned some upfront, but here is a slightly different kinds of list here. Astrophysics, where particles, the high-speed protons and electrons are impinging in space with all kinds of particles, and that would be interesting. Atmospheric chemistry, fusion research, where particles fuse under pressure. Nanolithography, sketching something at a very nanoscale level. Antimatter formation, and in medical applications like imaging analysis and treatment of cancers by some photo or other excitation processes. So with all those applications, so there need to be science that need to be developed, of course, based on mathematics. So there are this theory called an R matrix theory, where the space is divided into two regions. One is called internal region, close to the molecular system or the atomic system, and then a longer range where the electron can come. These effects have long range impacts from long range effects, and both local, internal and external effects need to be considered and to be treated to actually get the right answers for these kinds of problems. So I'm going to quickly go through some of these applications that were deployed through the gateway. So this particular application is called BSR. It's a B-spline R matrix method. So there is actually a workflow where initially some data is obtained from atomic and molecular calculations, either what we call Hartree-Fock or multi-configurational Hartree-Fock. Is a single configuration or a multi-configuration Hartree-Fock methods to obtain basic information about where the electrons are, where the protons are, and how they're interacting, what their energies are, and what the orbitals, where these electrons are stationed, or some description of these systems. And then some new electron from outside has to have impact on these, and then that need to be treated as well. And there is a series of procedures that are needed to go from the basic structures to the impact of other particles. And these workflow here is implemented for both relativistic and non-relativistic methods. So these relativistic mechanics are important, where you have to treat atoms and molecules that contain atoms of higher atomic numbers, like tungsten, iron, and so on and so forth. The non-relativistic ones or semi-relativistic ones are sufficient for treating like low atomic number species, like hydrogen or neon, and so on and so forth. And so the software, of course, all these application software were developed over tens of years. Some are a little bit more modern, some are, they have legacy. And so this this BSR application uses MPI for parallelization, and it uses both real and complex number mathematics, and so on and so forth. And so there's some very briefly some results. Just focus on that the solid red line, and these circles that shows that the results match with the experiment. In this case, for electron collision with noble gases, neon, argon, krypton, and xenon. And so there's another application called UK RMOL. And so this is coming from United Kingdom, contributed by Jimena Gorfinkel and the Open University with an OR matrix method again. And it has, again, its own workflows. So there is a input processing, and then a part of this is taken into an output processing to produce results that talk about resonance parameters, energies, cross sections, and so on and so forth. So there's again some results from the UKR mole. So the previous one showed impact of electron on rare gases. Here it is impact of electrons on larger systems, thymine with 5 water molecules on the top left, and a photoionization of nitrous oxide on the right. And these results, they look at details of various kinds of parameters that can be correlated quickly with the experimental data, and that is important. We're talking about being able to predict and use this in various kinds of applications, like in astrophysics and medicine and so on. A third application is this tRecx code, which is actually a more modern application. So the first two applications that I talked about used what is called time-independent quantum mechanics. And this code uses time-dependent quantum mechanics by solving this time-dependent Schrodinger equation, of course, with these strong fields. And there are different methods that it uses, particularly this anti-symmetrized, coupled channel methods, continuum analytic continuation by exterior complex scaling methods, and some of these, and the time-dependent surface flux methods. So the combination of this surface flux with the continuous exterior complex scaling together, tsurf and iRex, becomes tRecx, and that's how it's named. So the software is, as I said, is a little bit modern. It is actually was rewritten in C++ with a lot of recursive structures, and uses standard math libraries. It uses MPI for parallelization. It scales to hundreds of CPUs at this point. So again, the inputs, it uses standard inputs from Hartree-Fock or multi-configured Hartree-Fock systems, and then the structures allow in tRecx to easily post-process with Python and other modules. And of course, there's a CMake compilation that is available for this to make it easy to compile across many platforms. So another method is this convergent close coupling method. Again, this treats these long-range Coulomb interactions through potentials using surface integrals, and this theory, is recent in the last 10, 15 years, and it deals with single electron systems like hydrogen, lithium. Again, is charged lithiums and H2 plus and so on and so forth, and multi-electron systems. This theory is currently not yet available for molecular, large molecule systems. Water is where we where we are at this point, because it is treating with the surface integrals, which are computationally intensive. So there is some effort to actually distribute this computation in GPUs and so on and so forth. It uses, of course, frozen core Hartree-Fock Hamiltonians. So the frozen core means the inner electrons are kind of fixed. Only the outer electrons are treated as dynamic. Again, these results just to show that they can extract and extend the experimental results. They correlate well with the experiments and they provide additional data. As I said, this is being implemented on GPUs. Some preliminary speed up is just seen. If it is direct matrix elements with about 20 times speed up, and with exchange it is 10 times speed up. So depending on what the rate limiting step is, it is at least 10 times faster than the standard MPI code on GPUs for certain systems. And this we are using Comet GPU for some of these computations. So XChem is another code that also uses close coupling mechanisms. I won't go through this math, but the XChem uses open molcast for molecular descriptions. And as I said, this Hartree-Fock and multi-confident Hartree-Fock, both can be provided by a molecular application called molcast, which is actually a commercial product, but they have open sourced some of the basic things called open molcast, which becomes the starting engine for these applications. And so this treats what are called atom-centered Gaussians for the local ones, and the B-splines as the first original B-spline or matrix method was using. So by combining these two, the approach provides a way to treat these scattering on larger molecular systems. And so these results, for example, in this case, shows for diatomic oxygen. Of course, it is also implemented using MPI and OpenMP, and discretizes the space on the grid, and it is parallel in the sense. And molcast itself also is parallel, so the workflow is completely parallel. And so
Sudhakar,
yes.
Let me just cut in. We're at the bottom of the hour, and I want to make sure that we save time for a couple of questions and our second speaker.
So I'm going to quickly just quickly change and show maybe a couple of slides on the gateway, and then okay. I'll conclude. Yeah.
All right.
So okay, so just this is the application list. The gateway is provided by this Apache Airavata based middleware framework and hosted by SciGap. It is deployed here. So we have a way to provide the content and manage the content through a backtail based content management system embedded in the gateway. The user interfaces are provided through the Apache Airavata provided user interface definition mechanisms. Here I describe in this case the convergent close coupling on GPUs and Comet, as I mentioned. So all the required parameters can be embedded into these interfaces. So this is just another interface for the users to provide input. This is just a user interface that can provide workflows and multiple what are called file collections simultaneously as inputs. As see in the bottom, several inputs are provided. And so again, there are many interfaces here, and just there are a couple of things where you can actually have dynamic input interfaces. That means that interface can change depending on what the user adds to the as an input. And we can also follow the experiment once it is running on any resource like the XSEDE, Stampede2 or Comet. In this case, tRecx2 running on Stampede2, and the results are post-processed. using some flexible mechanism, either to see them as data or a graph or a plot in this case. So, I mean, there are more things about the output views. I mean, this I already mentioned. There is a storage that that brings back all the data and can be processed independently there. Again, just to summarize, this gateway is in production. It serves many applications. We have enhanced input and output processing possible. We conducted workshops with this. There are more workshops planned, but the coronavirus is disturbing some of these. But we will continue to do that once this problem is resolved. And there's more work. As I mentioned, some proposals are being written for sustainability and new integrations for pre and post processing. That's all I wanted to say. And any questions now or maybe at the end. I have.
Great. Thank you, Sudhakar. We do have a question from Mona. So Mona, do you want to go ahead and ask?
Hi, Sudhakar. I was just wondering, what is the most successful outreach effort that you guys have done to increase the user and usage of this gateway?
There's not too much effort. I mean, I would say it's a distributed among for example, this NIST workshop, which is a dedicated workshop for the atomic and molecular physics course. That was I think a single impactful workshop, I would say. But of course, there are presentations by various scientists involved in this, whose names are listed here, to present this in various conferences, the physics conferences, and there is some. I think I heard that for example, Igor Bray in Australia, he actually talks about this gateway in high school setting. So I mean, there are different kinds. So we are still, I think, early at this point. So I would say the most impactful was the NIST workshop, which actually generated adding new applications. There are new applications, new groups that are interested in providing applications that would go into this case.
Great, thank you. Everyone else on the call, please be sure to mute. I hear a little bit of background noise coming through. So Mona, I saw that you had another question. Let me ask you to follow up with Sudhakar offline on that, so we have time for our second speaker.
Yeah, sure.
Again,
thank you.
Everyone else, thank you so much, Sudhakar, for the excellent presentation. So if you go ahead and unshare your screen so that Igor can jump in. And again, please, everybody who's not speaking, mute.
Okay, hi everyone. So looks like I'm the next one. So let me share my slides. It should be this one. Let's see if it works.
Yes, he's made it. What a
Can you see them?
off the ground.
So can you hear me and can you see my slides?
Yep, we can hear you.
Okay, good.
Yeah.
So hi everyone. I'm Igor Sveligoy here at UCSD or San Diego Supercomputing Center. I work across many divisions here at UCSD. And I will go over what we did with IceCube. It was mostly an experiment, but doing real science in going into the public cloud and get a large-scale system out of it. And when I say large-scale, what I mean, the first burst was done just before supercomputing, and we got about 350 topic-to-bit petaflops of peak. Now, to get a sense of how big this is, if you look at the biggest HPC system currently deployed on-prem, which is Summit, that's about 100 petaflops. So we were almost into.
Excuse me, Igor, real quick. Xiaochen, please mute. We're getting your radio broadcast. Thank you. Go ahead, Igor.
So yeah, as I said, what we got from the cloud was almost the same as Summit. No fancy low latency networking, but IceCube doesn't care. So we for IceCube purposes, we got the equivalent of Summit out of the clouds without any special arrangements with them. We had to use 3 cloud providers, which is AWS, Azure, and Google all together. And we had to get resources from all over the place. We had about 30 regions total. And we had to use 8 different GPU types, anything from V100s, P100s, P4s, down to the ancient K520s. But you can do that. And if you can do it, you can get the equivalent of Summit out of the cloud.
Okay.
And what do I mean by burst? We went from 0 to the peak in about 90 minutes. But you see, it was not linear. The real initial peak, which get us to about 2/3 of or 20,000 GPUs out of 50,000 that we have at peak, happened in 10 minutes. So you can get to 20,000 GPUs in 10 minutes in the clouds if you just try. And again, let me stress that we had no special arrangements with the clouds to be able to do this. So it's available. Now, the first peak was really meant to be a peak. So we ramped up to the max and then ramped down quickly. But you probably don't want to do that in more practical applications. So we said, let's see what is possible if you want to sustain something for a whole day. So we did that in February, ran 9 to 5 essentially on a random Tuesday. And the first time we got any kind of GPUs we could get our hands on, second one said, well, let's be a little more careful about the budget. So we got only the GPUs that were most cost efficient, which we believe are T4s, P40s, and V100s. But even with this restriction, we were able to reach and sustain 170 32-bit petaflops for more than 6 hours and integrate over 1 exaflop hour of compute. And we spent about $60,000 doing this, which is not exactly spare change, but for an exaflop hour, it's not that much either. Now, we used preemptible or spot instances for all the GPUs because they cost about 1/3 of on-prem resources in the cloud. Of course, that gives you a little bit of waste, but as you can see from the chart on the right, it was less than 10%. And given that we paid 1/3 for the resources, I think that's a really good deal. And just to stress, this was not just burn CPU type of exercise. We actually ran real science in the clouds. In particular, we were running the ray tracing simulation for detector calibration from IceCube. And if you don't know what IceCube is a detector built at the South Pole to detect mostly neutrinos. Why the South Pole? Well, because there's a lot of ice there. So they instrumented a cubic kilometer of ice with optical modules. So when neutrino, which are notorious to not interact with almost anything, go through the ice and they go fast enough to exceed the speed of light in that medium, there is some cherry-like produced. Unfortunately, natural ice, while being very transparent, it's not homogeneous. It has a lot of impurities. It's shifting over time. So rays don't really go straight in it. So it takes a lot of calibration to actually get proper calibration of the medium in order to know where the particle went through. And on the right side there, you see one such light event simulated, and you see rays go anything but straight. So it takes a lot of jobs, compute jobs, to properly calibrate this natural medium. And luckily for us, GPUs are really good at ray tracing. Now, since this was a real experiment, it made sense to do it with a real production system. IceCube, it's already using HT Condor in production, both for dedicated OSG and XSEDE resources. So all we need to do was attach these cloud resources to this pool. To a certain degree, it was not a big deal because we really only doubled the number of slots that they have for the second run. But the amount of compute increased by 2 orders of magnitude. And the reason for that is that IceCube mostly have access to CPUs. They have only few hundred GPUs in their pool usually. And since you have one slot per CPU core, but GPUs are scheduled as a whole device, given that each GPU is really thousands of GPU cores, one GPU slot is about 10 teraflops, one CPU slot is really just 50 gigaflops. So that's 2 orders of magnitude difference. So even if we just double the number of slots, we actually completely obliterated the amount of compute with it. Now, full disclosure, we had to add some additional hardware to the pool in order to deal with the bursty nature of our exercise, because normally their pool is not that bursty, and the higher compute made for much shorter jobs. So there was much more churn to it. But that was about it, just a little bit of hardware. And the fact that they use HT Condor was great, because HT Condor is ideal for distributed computing. It's not mere coincidence that HTC is HT Condor, with HTC standing for high throughput computing, or like I like to call it, ingeniously parallel computing. Most Condor jobs are completely independent. There is really no native support for MPI or alike in Condor, and they require no share file system. HT Condor can handle file transfer, and for inputs and logs, IceCube uses that. Although IceCube for the large files does file transfer autonomously in the jobs, fetching data for their big central storage, and then pushing back the outputs there too. And I'm aware that not all problems can be expressed in this way, but a lot actually can. You just need to really think about how to properly decompose the problem to be in a lot of independent chunks. And once you do that, you can scale easily. As you can see, we went to 380 petaflops without a hitch, and we could have gone 10 times bigger if we got the capacity. HT Condor itself is also ideally suited for this, because its daemons are very flexible. They don't really need to be run as super user or root. They really don't expect much from the operating system, so you don't really need any special configuration. And they use strong authentication between all the daemons. So this implies that the networking is never trusted. You can go over the wide area network without any VPNs or any special arrangements. They will pretty much deal with whatever you throw at them. So going to the cloud was a no-brainer, because cloud resources are really not any harder than on-prem or bare metal nodes to add to a Condor pool, and definitely way easier than any grid resources that we get either from OSG and XSEDE. All you need to do really is launch an instance that contains Condor, do a little bit of configuration about the networking, because in cloud, the node itself doesn't know its public IP. It's essentially a reverse NAT kind of setup. And so Condor needs to know what the external IP is, because it cannot discover it by itself. After that, all you need to do is configure the security. In our case, we used the shared secret, but Condor supports many other mechanisms. Point it to the central manager, which happens to be the HT Condor collector, and start the daemons. And you're done. Things just start to work from there on completely autonomously. Let me just point out that using a public IP with incoming connectivity, it's not strictly required for Condor. We used it because clouds allow us to, and Condor, it's actually way more scalable if you do it. But pretty much anything on OSG and XSEDE doesn't use that and works just as fine. So that's about the general structure. Now, how did we go about provisioning these cloud resources? Let me be upfront. Cloud provisioning tools do exist. We just didn't use them. And the main reason why we didn't use them was because actually going straight the cloud native way is so easy. But nevertheless, if we wanted to use, there is Glide WMS, which is a de facto HT Condor provisioning system from OpenSense and be used extensively there. And it has some support for clouds, but as far as I know, hardly anyone ever uses. So we didn't want to test our luck trying something that really almost nobody uses. HT Condor itself has something called NX, which is native to HT Condor. It's supposed to be very great for scaling to getting small bursts, but really has never been exercised at such large scales before. So we didn't want to have to debug one more interface with, in the process. And I'm also aware of something called the Cloud Scheduler, which is a tool that comes from Canada. Their authors claim it's the best thing under the sun, but they are really the only ones that ever use it. So we didn't want to be a guinea pig. And as I said, cloud native instance launching is so extremely easy that we said, why bother to check for third-party tools that will just add one more thing that can go wrong? How easy it is to launch a cloud instance? It's actually pretty trivial. You just go to their site and select an image, select the kind of resource you want, and click provision, and it's done. Literally as easy as that. So it's great for prototyping. However, if you want to provision hundreds or thousands of instances, you probably don't want to point and click. So you want something better. Luckily, there is cloud native grouping mechanisms that are provided out of the box. You just have to define the template once, and you can even do that with their web portal without scripting. I did most of that just through their web portals. And then you can launch hundreds or even thousands of instances with either a single click or a single command line invocation. Now, different cloud providers use different names for these mechanisms. AWS has fleets, Azure has virtual machine scale sets, Google Cloud called them instance groups. Their semantics, while not identical, is very similar. So once you learn one, the other two come pretty naturally. And here I have a snapshot of how it looks like in Azure. You create this thing called the virtual machine scale set. And once it's done, in order to increase launch, let's say 194 instances, you just click on a slide bar and say save, and it will do everything else for you. If you like scripting, it's a line like this. Really, all you need to provide is the name of the scale set and how many you want. And it will do everything for yourself. Now, unfortunately, there is no one cloud. When people talk about the cloud, there is really no such thing. What you have is a lot of independent cloud regions. And this is even within the single vendor, and there are many vendors. So up here, I have a snapshot of what it looks like for AWS. Here I have a snapshot of what it looks like for Azure. There is an equivalent map for Google and for the other cloud providers. There are not just those three, although we use just one three. And something to really be aware of is that each region is pretty much configured and provisioned independently. They are pretty much independent between them. And we had to get about 30 during our big burst to get all the available capacity that was in there to get to the 380 petaflops. So once you have tens of different regions that are completely independent, pointing and clicking it's not an option anymore. So you have to do some scripting, but it's really just a for loop. So something as easy as bash, it's all you need. And I did most of my stuff just in bash without getting into any more complicated tools than that. Now, public clouds allow you to install any software you want, because cloud is really infrastructure as a service, which means you're just renting the hardware from them. And they make it really, really easy to do that. But the software, it's all up to you. You have to pick the whole software stack that from the OS, batch systems, compiler, everything. It's all up to you. This is a different point of view from what most HPC centers or even grids provide, because the HPC and grid is really platform as a service. So it provides way more than just the hardware. Although with all this container buzz going on, this difference is getting much, much smaller, since containers are essentially just virtual machines without the virtualization. But you have to do a little bit more when you go to the cloud. Cloud providers will give you a lot of pre-configured images already out of the box, but you don't have to use them. You can bring your own. And if you are a novice user, this can be quite challenging because there are literally tens of thousands of pre-configured instances or images already there if you want to use them. But if you know what you're doing, it's really great because you can get exactly what you want. And in our case, we created an image that contained an OSG worker node, mimicking as close as possible what an OSG worker node would look like, slapped HT Condor daemon on properly configured HT Condor daemon on top of it, launched it, and we were ready to go. It's really as easy as that. Just remember, there is no one cloud, so when you create an image, you have to replicate it across all the regions. It's actually pretty easy within a single cloud provider. Microsoft Azure has something called shared image galleries that allow you to do this very easily. Google allows you to create images that span the whole continent. AWS, it's a little less easy, but not that hard either. What it's not present is a native way to share images between different cloud providers. So we went ahead and create one image for each cloud provider, also because we want to make them slightly different, because even though cloud is more or less homogeneous, there are subtle differences between cloud providers. So it actually makes sense to have different images for the different cloud providers. But once you have an image in one region, distributing it across all the other regions is pretty much trivial. So that's all I have about the setup itself. Let me just switch slightly gear and talk about networking, because you definitely need some kind of networking to move data around as soon as you have more than one node, and we had tens of thousands. Luckily, public cloud providers have really great networking in place. I've made a bunch of tests before the bursts because we wanted to make sure that we were not wasting compute waiting on networking. Here you see what you can get inside a single region if you go to their object storage. And you see I almost got to 2 terabits per second, and it's not curving. I probably could have gone beyond that. I just stopped there. I measured between region network bandwidth anywhere between 100 gigabits up to 1 terabit. Google is really good at that. And when you want to get data in and out of the cloud to the on-prem, 100 gigabits these days, it's pretty normal, as long as your on-prem infrastructure can support it. Down here, you see reading from several nodes, data from Azure object storage. And here you see the opposite, a bunch of cloud instances reading from web servers at University of Wisconsin-Madison. In both cases, you see I exceeded 100 gigabits per second. These are gigabytes. Now, once you use networking, you have to be aware that you may be charged for it. All incoming and in-region networking is free. So this two didn't cost me anything apart from what I spent on running the cloud instances. But once you get data out of the cloud, you start to be billed. And the cost is anywhere between $20 and $120 for each terabyte you transfer. The difference is depending how you do it and from where to where. So if you're transferring petabytes, then that starts to be expensive. For a few terabytes, it's usually in the noise. And especially if you compute a lot. And moreover, if you compute a lot, and up to 15% of the bill can be spent on networking and be completely waived by the cloud providers. And just to give you an idea how much this is, even running in Spot, for each hour of V100 GPU, you get 2 gigabytes free, which for a lot of applications is actually more than enough. Not all of them. Some are more data intensive, but a lot of them can actually fit in that envelope. And this is 15%. If you go past, I would say if you spend 20 or even 30% on networking, well, if it's worth it, if you need it, you need it. But in our particular case, this didn't end up being a problem because we chose a compute workload that was compute intense, so light on data. And we did this on purpose because we really were interested mostly in compute, and we didn't want to be worried about networking. But we do plan to try again with a more network intensive or data intensive exercise in the future. We just didn't do that. But even in this case, the second run, we used about 4 gigabits per second bandwidth out of UW Madison, which is an order of magnitude less than what that machines can pump through. But still not negligible. But we were definitely not pushing it, and you can see the download times were in seconds out of a runtime of tens of minutes for the jobs. So we really were not wasting any time whatsoever on network transfers. It was all compute. So that's pretty much all I have. And just to conclude, let me ask a question. Should anyone copy what I did? And the question is really what you want to do. I would like to remind you that our setup was meant to be an experiment. We just wanted to see how much is available in the cloud. Long-term sustainability was never a concern for what we did. It was a one-off setup. We had no procedures in place to keep it up with patches and stuff like that. We essentially created it and destroyed it. We had rapid, bursty, manual provisioning and deprovisioning. It was definitely not on-demand driven, also because IceCube have pretty much infinite demand. So we could run there for weeks or months if somebody would pay for the cloud bill. So demand was never an issue. So keep that in mind. But it was definitely low human effort. I could recreate what I did in a day, maybe two, from scratch, and any day. So if you're planning to do a one-off burst into the cloud, or do it rarely, like once every 6 months, I would definitely recommend go the cloud native way. It's just so easy, and you know exactly what's going on, that it makes perfect sense. But if you plan to do something a little more steady state and the demand based, cloud provisioning tools are probably the way to go. And I said there are several of them, but it was not our use case. So that's what I have. Here are the standard acknowledgements. This was not all just me. It was Frank, David, and Benedict helped a lot. And we had support from NSF and also some credits from the 3 cloud providers for the network testing. So if you have questions, I'm more than happy to answer them.
Great, thank you, Igor, for the wonderful presentation. And we do have a bunch of questions lined up. We're going to start with Carl. Did you want to go ahead? So this is from Carl Barabal. Okay, I guess Carl had to drop off. And Rick McMullen, are you still on?
I am indeed. Can you hear me?
Yep, we can hear you. Go ahead and ask your question.
Okay, so Igor, did you put any thought into sizing your images and dealing with any trade-offs between, you know, the sort of set cost for an instance with a certain number of cores and memory, or did you just say this is sort of a default size that we've used before commonly in OSG, and we'll just do it that way?
So for yes and no. So for the first cloud run, we didn't care. We just wanted to see how much we can get, cost be damned. So we really didn't care about it. After we finished the first run and we saw how much it cost and what's available, as I said, for the second run, we only used the most cost-effective ones. And really, the cost is all driven by what kind of GPU you have. Memory and CPU, it's not an issue. The difference between the more memory or less memory on Google is negligible. For AWS, for Azure, you have no choice. For AWS, the only choice you have is for the T-Force. And indeed, we used only the cheapest of the T4s, which is the smallest instance. IceCube really only needs 1 or 2 cores and a few gigs of memory for each GPU that it to drive the GPU, and we couldn't go smaller than the smallest instance that we got for that. So it's really not, you don't really have much choice.
Right, excellent. Thank you. Just going to go back again. Carl, are you available? Okay. So I'm going to go on to a question from Anita Schwartz, and she asked me to ask the question. This is based on HT Condor, high throughput versus high performance. Sorry, your use case is based on HT Condor, high throughput versus high performance computing.
Right.
Correct.
So
can you comment on a use case or experience for the latter HPC? Oh, go ahead.
So I'm well aware that not all problems can be solved in HTC mode. I have been working on the fusion simulation with General Atomics, and actually we are in process of running a cloud simulation with Fusion, which is HPC. It's essentially an global FFT transform. You cannot do that without really low latency. It will just kill you. It's network bound. So anytime you have a problem that is inherently latency bound, you are stuck with pure HPC, and you absolutely need low latency because you have to. But I have seen enough codes that were MPI just because that's all this, their developer knew, and they were using MPI just to exchange data once every few minutes, and we would block on that without any good reason. So that's why I'm saying a lot of times you can split applications to be pretty much independent if you think carefully about it. And in those cases, you can get way better scalability because you can do stuff that change the number of nodes, that have high latency, and stuff like what IceCube does. It absolutely fits the HTC paradigms because each ray tracing experiment is completely independent.
Thank you, Igor. And we,
So
do you mind staying on? Oh, yeah. Go ahead. Go ahead.
Just answered. What fraction of what the credits? The credits were used just for the testing. So all the real stuff was done, was paid by NSF. It was not paid with any credits. The credits were only used for network testing. That's what the credits are earmarked for.
Okay, and we also had a question just before that from Amit Shirazia. So could you guess the equivalent cost for 1 day of Summit run based on any cloud provider cost for similar workload?
Well, the problem is Summit doesn't cost anything because the cost is proportional to the human time to get an allocation. No, I don't have that. But I would actually consider, given how much of the cost of Summit is actually the networking, it may actually be comparable because we don't care about networking. But no, I don't know.
All right.
My question was, if you take the cost of the GPU nodes on any cloud provider and kind of come up with a number for Summit, or for that matter, any other XSEDE or OSG system, what would the cost structure look like? Because currently this cost is being paid by someone, right, on XSEDE, OSG, or Summit.
Yeah, we did some cost analysis on-prem versus cloud. And if you use the same type of GPUs, it's probably cloud in preemptible modes. If it's about 1.5 the cost. If you can go with the gaming GPUs, it's anywhere between 5 and 10 times cheaper to do it on-prem, because cloud providers cannot use gaming GPUs. Some sites, some universities can get away with it, and gaming GPUs are really extremely cost-effective. 2080 is pretty much as fast as a V100 and costs about 5 times less. So it really depends what you compare. On identical hardware, it's probably 1.5x, including human support and electricity cost. If you take just the cost of hardware without operations, it's probably cloud is 3 to 4 times more expensive. It really depends what you put in the equation. We have been, some in my group have been trying to come with a good number, but it really depends what you count in. There are so many parameters, and here you pay by the second. When you buy, you essentially buy it and have to run it for 3 to 5 years. And can you keep it busy 100% of the time? Do you compare against a 70% utilization and so on? There are so many parameters.
All right, thank you, Igor. Now I see that we've gone well past the top of the hour, so I'm going to make that the last question. Thank you, everybody. Thanks to both of our speakers, and look forward to seeing all of you at next month's ECSS Symposium.
Okay, thank you.
Thank you.